I guess I'm audible. So, hey guys, I'm Ruthvik, and in this session, I'm going to discuss the problems from LeetCode Weekly Contest 487. Okay, so coming to the first question, the name of the question is Count Monobit Integers. Here, we are given an integer n, and we call an integer monobit if all bits in its binary representation are same. So we have to return the number of monobit integers in range 0 to n. I'll go through one of the test cases here. When the value of n equal to 4, the integers in range 0 to 4 include 0, 1, 2, 3, and 4. These are in binary representations, and here we can see that 0 is a monobit because it contains only 0 as bit in its binary representation, and also 1 is a monobit because it contains only 1 in binary representation, and 3 is also a monobit. It contains only two ones. So 0, 1, 3 are monobit, satisfy the monobit condition. So the answer for n equal to 4 is 3. So here our observation is we have to count the number of monobit integers which are less than or equal to n. So first observation is the 0 is a monobit integer, and the monobit integers are I'm writing in binary representation. They contain only 1 or 0, right? If they contain only zeros, then the number that is formed is 0. Only zeros in binary representation. If they contain only 1 in binary representation, then the numbers are as follows. This is 1, this is 3, this is 7, and this is 15. Basically, any number of form 2 power n minus 1 contains only ones in its binary representation. For example, this is 2 power 1 minus 1. 3 is 2 square minus 1. 7 is 2 cube minus 1. Similarly, 15 is 2 power 4 minus 1. 16 minus 1. So here what we can do is that hmm, suppose initial I am currently at value 1, that is 2 power 1 minus 1. So in order to get next monobit, uh, or 1, or I'll generalize the case, I'm currently at 2 power x minus 1. So in order to get next monobit, what I'll do is, I'll do current plus 1, which is equal to 2 power x. Next what I'll do is, I'll multiply this by 2. So 2 into 2 power x, which will be equal to 2 power x plus 1. 2 into current plus 1. After getting this, after getting this, what I'll do is, I'll subtract it by 1. So what will happen is 2 power 2 into current plus 1 minus 1. So let's suppose if this is our current monobit, in order to get the next monobit, what I have to do is 2 into current plus 1 minus 1. Because if if the next one after this is 2 power x plus 1 minus 1, right? So I can get 2 power x plus 1 minus 1 by doing this to the current number. So simply what I'll do is, mm, I'll keep on doing this until I am less than or equal to n, and I will maintain a count of number of integers while I'm iterating. So I can explain this better if I show the code. So here, if n equal to 0, then I'll return 1 because n equal to 0, the only possible answer is 0. So coming to the other cases, here let P be the current monobit. The smallest monobit integer is 1, right? And the count is 1. So what I'm doing here is while 2 into p plus 1 minus 1 is less than or equal to n, this is nothing but 2 into current plus 1 minus 1, which we have discussed earlier. While this value is less than or equal to less than or equal to n, I'll increment it to the next monobit, and also I'll increment the count. So I will keep on visiting all the monobits until they are less than or equal to n, and my count gets incremented every time. So finally, what I'm doing is I'm returning 1 plus count, because here the count contains only monobits that contain all ones, and this one extra one is for 0. And that's all. This actually the time complexity of this solution is log n. We can also do a simpler this question also allowed O of n constants because the value of n is 1000. So we can simply iterate over all the integers, but this solution is a bit more optimized because here every time p almost gets double. So this loop runs only for log n times. In the case where n is 1000, this loop runs for at most 10 times. That's all. So coming to the second question, the name of the question is final element after subarray deletions. So we are given an integer array. Two players, Alice and Bob, play a game in turns, with Alice playing first. In each term, the current player chooses any subarray such that R minus L plus 1 is less than M, which is like M is the current length of the array. Here, the condition they wanted to impose is that the subarray size should be less than the length of the array. Basically, the player cannot choose the entire array in his turn. Then the selected subarray is removed. The remaining elements are concatenated to form the new array. The game continues until only one element remains. Here, Alice aims to maximize the final element, and while Bob aims to minimize it. Assuming both play optimally, return the value of final remaining element. So, coming to this, like I'll go through one of the test case. Here in this, what Alice can do is Alice initially removes 1. So the array becomes 5 and 2. As Bob wants to minimize the array, last element, so Bob removes the element 5. Because if he removes the element 2, the remaining element will be 5 and it will be greater than 2. So Bob removes 5 so that the remaining element will be 2. So the answer is 2. So here the final element is 2. Similarly, in this case, Alice removes the element 3 because as she wants to maximize the remaining element, right? If she removes 7, then she will be left with 3. So it's optimal if Alice remove the element 3, then the element 7 will remain in the array, and the final answer is 7. And here we can note that Bob cannot play a turn now because the array contains only one element. So the final answer is 7. So coming to the explanation, let this be our let this be the given array. So here the first question is that let's suppose mm, Alice has the power to do this, like she can remove all the elements except the first or last one. In this case, she can remove A2 to A5, so only A1 will be remaining. Or she can remove A1 to A4, so only A5 will be remaining. So Alice has the power to do this. Like basically in one turn, she can remove n minus 1 elements and Bob gets no turn. And the final element will be a1 or a5. So max of a1 comma a5. If a1 is greater than a5, then Alice removes a2 to a5 so that a1 will remain. And if a5 is greater than a1, she does the reverse. She removes a1 to a4. Okay, so this can be our answer. So here the another observation. So here the question is that if there is any element in between a1 and a5, let's suppose a3. A3 is greater than a1 and a3 is greater than a5. If let's see if Alice can bring this element to the final answer, like make this the final element in the array. So for that, in what she can do is she cannot remove this element, right? So she will either remove some elements from here or some elements from here. But if such a case is possible, then what Bob will do is that if Alice removes from left side, then Bob can remove all the remaining elements. Like for example, if Alice remove just A1 in the first turn, what Bob will do is Bob will remove all the remaining elements so that he doesn't want A3 to be the final answer. So Bob can always ensure that Alice can't make a number in between A1 and A5 as final answer. So here the final answer will be either A1 or A5 because Bob can always stop Alice not to do this. And let's suppose in some case there is a number between A1 to A5 which is smallest. If this is smallest and if there is uh, what Bob wants to do is that Bob wants to make this the last element, right? But we can note that Alice can always stop this. Like at first turn itself, Alice can remove all the subarrays such that A1 or A5 will be remaining, right? So if there is a solution where A2 is a last element, Alice can always stop that because she can remove this element in her first turn itself. So here we can see that Bob also can't force a number in between A1 and A5 to be final answer, to be final element. So here we can note that either A1 or A5 will only be our final answer. If the array is A2, A3, so on till A5, either first or last element. As this is, as in first turn itself, Alice can do this. So Alice will obviously choose the element which is higher. Like Alice will make sure that the element which is greater out of both of them will remain finally. So our answer will be max of A1 comma A5 itself. And this is A1 comma A5 is basically the first element in the array, and this is the last element in the array. So the solution of this question is just one line. What we are doing is we are given integer array, we are given a vector, right? So our final answer is this is the first element in the vector and this is the last element in this vector, and I am returning the max of those two elements. And that's all. So coming to the third question, we in this question we have to design a ride sharing system. Here Here, the ride sharing system manages ride requests from riders and availability from the drivers. Riders request rides and drivers become available over time. The system should match the riders and drivers in the order they arrive. Okay, this is just some basic intro. And we have to implement the ride sharing class. Here, the main part comes. The ride sharing system initializes the system. Here we have a function add rider. What this function does is it takes the rider ID, an integer as input, and adds the rider with given rider ID. And here add driver. This function also takes an integer input, the ID of a driver, and what it does it adds a driver with driver ID. Here we have another function int match driver with rider. What this does is it matches the earliest available driver with the earliest waiting rider and removes both of them from the system. And it returns an integer array of size 2 where result equal to driver ID, comma rider ID. If a match is made. If no match is available, like for example, if there are no riders or if there are no drivers, then match formation is not possible, right? So I have to return -1 comma -1. Now here we have another function where cancel rider, where in the, what this takes the rider ID as input, this function, and what it does is it cancels the ride request of the rider with the given rider ID. If the rider exists, Uh, so only this happens if the rider exists and has not yet been matched. Okay, I'll explain the question. Here we have riders and drivers. Let the riders be of ID 1, 2, 3 and drivers 3, 4, 5. Or the IDs are random, right? Let's suppose initially all the riders and drivers are empty. So for example, here a rider with ID 2 comes, 3 comes, and 5 comes. After that, a driver 6 comes. What happens here is, after a driver comes, we can see that a match can be made. Like a rider 2 has arrived first, and driver 6 has arrived first. So match 2, comma 6 is made. Let's suppose driver 10 arrives next. 3, comma 10 is made. Driver 15 arrives. This is made. Like that, uh, some another rider 15, 20, or let's suppose in this case a driver arrived next, some driver number 21 and also driver number 6. He has finished the earlier ride with number 5. He arrived again. And driver number 13. Here, let's suppose another rider arrives. So he forms a match with the next available driver. That is driver number 20. So basically, let us solve a easier version. Here they have told the void cancel rider, right? Let's suppose this function is not there. So in this case, what we can do is we want a data structure that takes all the rider IDs as input, and it can return the ID of the first rider. Or I'll generalize the data structure that takes all integers as input, like we can push in it, and it has to return the first element that came in that has initially arrived in it. So obviously for this, the best data structure is Q. What this does is I can simply push the rider IDs, and if I query q dot friend, then this will return the first integer that I have pushed in the queue, and I can simply pop it. after processing it. So if there are no deletion queries, what I'll make is I'll make two queues, one queue for rider and one queue for drivers. And I will, when I add a rider, I'll push in rider queue. When I add a driver, I'll push in this queue, the rider ID and driver ID. And when I am asked to make a match, what I'll do is I'll take the first element from each of the queues. From each of queues. Queue, and pop them. Uh, so if either of them are empty, then our answer is -1. Else, our answer is x comma y, where x is the first element from the rider queue and y is the first element from the driver queue. And we are also popping these elements. As here they have told that we have to match the earliest driver with the earliest rider, and we have to remove both of them from the system. So basically, removing this, popping them removes them from the system. So this solution will suffice if there are no deletions. Like here, we have to cancel rider. Basically, we also want to delete from this queue. Okay. If so, the problem here is that if the element is somewhere in the middle of the queue, we can't delete them quickly. Like it takes so often time to delete an element which is in middle of a queue. So for this, what we can do is that in order to simulate deletions, so what we can do is that instead of maintaining a queue of int, I'll maintain a queue of pair int comma int for rider. What I'll be pushing in this queue is that I'll pushing I'll push rider ID comma time. Like basically I'll maintain a timer initially, and I'll keep on incrementing the timer each time when I add a rider. So for each element I'll push the rider ID and the time at which he has arrived. Okay. So if there is a deletion, like if I have called a delete rider function, what I'll do is I'll initially check if rider exists or not. If rider with that ID exists, what I'll do is that I will push the rider ID, comma, time at which he has arrived in a set. Push it in a set. Why I am pushing it in a set is that while accessing the queue, while accessing the top element of the queue, basically rider queue top element. Let the name of this set be the rival left the system, right? So left let the name of this set be left. Okay. So while accessing the element from the queue, what I'll do is I'll check initially if the element is in set or not. If the element is in set or not. If the element is in the set, then I'll simply pop the top element, and I'll keep on popping till top element is not in set. Okay. So finally, I'll get an element from the queue. such that it is not in set, then I'll take this as the current rider ID. The reason why I am keeping timer is that, let's suppose in the queue, if suppose let the riders be 1, 2, 5, 7, 8, and let's suppose the rider 7 left. And after some time, the rider 7 arrived in the queue again. So in order to differentiate these two empties, here, if I keep a timer, then the time here will be 1, 2, 3, 4, 5, 6, 7, 8, 9. So this entry will be 7, comma 4, and this entry will be 7, comma 8. So while checking if the top element is in the set or not, if I reach here, I can safely assume that this element has the rider has left at this point of time. And if it is 7, comma 8, then this element will not be in the set. Then I can tell that the rider is there at this point of time. So in order to differentiate these two empties, I am pushing the entries in the form of rider ID, comma time in the queue. I guess I can explain better with the code. So here, initially for driver, simply a queue of int will suffice. So this queue int contains all the driver IDs. And for rider, queue pair int comma int, we are using pair of ints of queue for rider. Now, and also a set for all the riders who have left the system. I will push in the set. And also I have maintained the variable timer. And here the map int command time basically records the time for the rider, like for every rider ID, the time at which this rider has arrived. So here initially while I am adding a rider, I will increment the timer and I'll push in the rider queue. And also I'll update the time for this rider. Why now in the add driver function, simply I'll push in the driver queue. In order now for the function where we have to match driver with rider, initially our answer is -1, comma 1, while rider queue is not empty. I'll take the first element in the rider queue and I'll check if the set contains this element. Basically, this set contains all the list of the riders who have left the system. So I'll check if the current rider has left the system at that point of time. Basically, rider comma time, this pair is present in the set or not. If this is present in the set, I'll pop this from the queue. Else I'll break it. If it is not present in the queue, that means that the rider is present in the system. So I'll break this while loop. Next, what I'll check is if either rider queue is empty or the driver queue is empty, then the answer will be -1, comma -1. As initially this value is -1, comma -1, we can simply return the pair. Else, what I'll do is the first element is the driver ID, right? So the first element is the top element of the driver queue. And the second element is the top element of the rider queue. Here I am taking the rider queue dot first because in this queue I am pushing in the format of rider ID, comma timer. Second element is timer and the first element is the ID of the rider. So rider ID, the top element in the rider queue dot first, and I am popping, like basically after assigning the values, I am popping them from the queues. Uh, uh, Right, that is removing both of them from the system. And next, what I'll do is I'll return these two values. So finally, coming to the function cancel rider, here I'll check initially if the rider is in the system or not. Basically, if rider is in the system, what will happen is that I am making an entry in this map, right? So if time dot contains rider ID, if rider is present in the system, I will insert the element rider ID, comma time at which the rider arrived in the set. And next, what I'll do is I will erase the current rider ID from the map, basically this time map, so that next time if I encounter this function again, this will return false because already I have removed the rider here. So here I can safely remove it from this map. And that's all. The time complexity of this solution is n log n because uh, like every function takes at most log n time. Here, this add rider function takes log n time because we are making an entry in the map, and this function takes off one time because we are just pushing it in the queue. And while matching, this function also amortized time complexity will be log n for this function. Basically, if there are n calls for this function, it will take n log n time because we are removing the elements from the library initially, which have already left. And after that, we are finally returning the top element. Log n comes because of this call because we are checking if the element q is there in the set or not, and this takes log n time. And after that, this function also takes log n time. So total, if n calls are made, the time complexity will be n log n for this solution. And coming to the last question, here we have to find the longest alternating subarray after removing at most one element. We are given an integer array, and subarray of the array is called alternating if one of the following holds. Like for example, at index L is less than L plus 1. Like the array element at L is less than L plus 1, and which is greater than L plus 1 is greater than L plus 2. Basically, the signs will keep on alternating. Like here, greater than sign, then less than sign, then greater than sign, then less than sign. So this is the definition of an alternating subarray. After that, what we are doing is we can remove at most one element from the given array. Then we have to select an alternating subarray from the given array, and we have to return the maximum length of that alternating subarray that we can select. And also here we have to note that the subarray of length 1 is also called alternating. Like for example, in first test case, here we can see that 2 is greater than 1, 1 is less than 3, and 3 is greater than 2. Here the symbols are alternating, greater than, less than, and greater than. So here it's best if we choose not to remove any elements, and the output will be 4. That is the size of the entire array. And in the second test case, here nems 3 is removed. That is the final array will become like this. And out of that, we can see that this is the maximum alternating subarray. And size of this subarray is 4. So our answer is 4. So coming to the explanation. So either if array is like this or if array is like this, the signs must be alternating. That's all. Then we can call this an alternating subarray. Alternating subarray. So here the first question is that if uh, like we can calculate whether we can calculate for every index the longest possible suffix or prefix that is alternating. Like initially, let's start with the longest possible suffix that is alternating. For example, if I am at element I, Then uh, like here I'll calculate the longest possible prefix. If I'm at element I is all has only one element, so it is alternating. So if we consider I to I plus 1, if AI is less than AI plus 1 or AI is greater than AI plus 1, then size 2 is alternating. So on, if I to I plus 2, I plus 3, I'll keep on checking the maximum index j such that I comma j is alternating. Subarray A of I comma j is alternating. I want to calculate the maximum index j for all I from 1 to n. Basically, the maximum size of alternating subarray starting at index I. This can be calculated using DP. Like for example, if DP of I contains the maximum size of alternating subarray starting at I, what we can do is the transition will be as follows. Like for example, if we let's suppose we are coming back from the suffix, dp of n minus 1 will be equal to 1. N minus 1 is the last element, so as it is of size 1 and we have no other option. Like for example, 1, 2, so on, n minus 2, n minus 1. These are the indices of n minus 1 is the value. So here we have no other option other than to take just this one element. I'll write the definition of dp. Max alternating subarray size dp of I starting at index I. So for index L minus n minus 1, our answer will be 1. So for any general I, what I can do is dp of I equal to mm, if ai is less than a of I plus 1 and a of I is less than like a of I is greater than a of I plus 2, or a of I is greater than this and this is less than this. So if this condition is satisfied, so the value of my dpi will be 1 plus dp of I plus 1. Because if this is satisfied, I can safely append my element a of I to already existing alternating sequence that is starting at I plus 1. So my answer is 1 plus dp of I plus 1. And the second case here will be if a of I is if a of I is equal to a of I plus 1, then I cannot take like it is impossible to append my element a of I to sequence that is starting with I plus 1, because here in the alternating definition we are given that uh, the inequalities must be strictly less than or strictly greater than. So equal to sign should not exist. So if this case occurs, then my answer will be dp of I will be equal to 1. If this is not the case and this is also not the case, then here the case is as follows. Initially, initially this a of I is either less than or either greater than a of I plus 1. But this condition is not satisfied. Like for example, here if a of I is less, here also there may be a less than sign, or if here it is greater, here there is a greater than sign. So this is not satisfied. So in this case, my answer will be dp of I equal to 2, because dp of I can contain a of I and a of I plus 1. Because starting at index I can have the subarray containing ai and ai plus 1. So in this case, my answer will be 2. So in that way, we can calculate the dp. This is what the dp where I have written the definition earlier, right? The max alternating subarray size starting at index I. Similarly, we can also calculate the max alternating subarray size here ending at index I. This also can be done using DP. Like I'll explain both of the DPs first with the help of code. Here I am coming from n minus 2 to 0. Initially, I am calculating the first DP, where SDP means the suffix. As I am coming from suffix, I have named it as SDP, suffix DP. So this contains, SDP contains max alternating subarray size starting at index I. Here, what I'm checking is if AI is less than A. Initially, I'm initializing all of them with 1. If AI is less than AI plus 1, what I'll do is I'll check if the condition is satisfied at AI plus 1 also. If it is satisfied, then my answer will be DP of I plus 1 plus 1. Else, my answer will be 2. Here we have discussed both of the cases, right? Here, DP of I plus 1 case, 1 plus dp of I plus 1 case, and here the case where dp equal to 2, and where if a of I is less, here this is less than case and here this is greater than case, and if a of I is equal to I plus 1, then our answer will be 1 itself. As I am initializing the array itself with 1, then that will remain as it is, no change. So similarly, in this way, we have calculated the first TP. Now calculating the next one, what this signifies is max alternating subarray size ending at index I. So for calculating the subarray starting at index I, we have come from reverse, right? Like from I equal to n minus 2, we have come from there, right? And I equal to n minus 1 will be 1. So I have not bothered to start the loop from there. So for calculating the max alternating subarray size ending at I, what I'll do is I'll start with index 1 and I'll check if A of I is less than A of I plus 1, and similarly here I'll check the previously the condition is satisfied. The transition will be same here as we have done in the initial suffix dp. So here dp of I will be equal to dp of I minus 1 plus 1. Else the value of dp of I will be equal to 2. Here it is same as we have done before. The proof is also pretty much the same. And in the case where this a of I is greater than a of I plus 1, we are checking if a of I is less than a of, like I minus 1 is less than a of I minus 2. Basically, I minus 1, I minus 1 and I2, I minus 2, I am checking whether it's alternating or not. If it is alternating till I minus 2, then dp of I will be equal to dp of I minus 1 plus 1, else the value will be 2. In this way, I have calculated the prefix and suffix dp. Here, initially, I am setting the answer to the case where I am not removing any of the element. Then my answer will be simply the maximum value in the in both the dp arrays. So I have taken the maximum element of the first dp array and the maximum element of the second dp array, and initially I have initialized the variable answer with the maximum of these two values. After that, what I am doing is I am removing, I am made, I am going over a for loop where I am selecting the index for the removal of the element. I'll discuss this now. What Now we have calculated the prefix and suffix TP, right? And STP. So what I am doing now is I'm checking the case where I am removing all iterating over I, and I am calculating the answer if we remove AI from the like basically if we remove AI from the array and then calculate the answer. How we can do this is that, let's suppose 1, 2, 3, 4, or I'll generalize the case. Let 1, 2, so on. I'm removing some element I minus 2, I minus 1, I plus 1, I plus 2. Okay. I am removing this element. So what will happen is that here I'll check if a of I minus 1 is less than, like if uh, a of I minus 1 is less than a of I plus 1. I'll do some casework here. If this condition is satisfied, then I'll check the alternating condition. If a of I plus 1 is greater than a of I plus 2, then what I can do is I can take, like here PDP contains the max alternating subarray size starting at index I, right? So if this alternating condition is satisfied, I can simply take the PDP of I plus 1 here. If this is satisfied. Else what I'll do is I can only take the element ai plus 1. So I can only take one element from this side, like I plus 1 side. Similarly, for how many max elements I can take from I minus side. Basically, what I'm doing is I'm checking how many max number of elements I can take from this side and max number of elements I can take from this side after removing this element I. So here similarly I'll check if a of I minus 2 is greater than a of I minus 1. If this is satisfied, then the alternating condition is satisfied, right? Because here we are having a uh, here we are having a greater than, here we are having a less than symbol, so alternating is satisfied. If this is satisfied, what I'll take is, I can take here SDP of I minus 1 elements. Because what SDP contains, oh sorry, here HTTP contains the starting at index I, right? So here not PDP, I have to take HTTP of I plus 1 starting at index I. And here I am taking PDP of I minus 1 because PDP gives the max alternating subarray size ending at index I. So I'll get the max size ending at index I. Else, if this condition is not satisfied, just I can take one element from the left side. Basically, I'll sum up these two. Sum this and this value. The max element I can take from left plus max element I can take from right. I'll take the sum of these two. In the case yeah, and pretty much this is the answer. So here I am iterating over the index for the element that I am gonna remove. And if AI is less than AI minus 1, I'll check if the alternating condition is satisfied. Oh, sorry, not here. This is the calculation of PDP, right? Here I'm iterating over the elements that I'm going to remove. And here we can note that it's useless if I remove the first and last element because removing the first element uh, does not give us any significant advantage because there is no way we can extend the array to left side of the first element as there are no elements, right? So it's useless if I remove the first or if I remove the last element. So basically, I'm iterating over all the middle indices from I1 to I less than n minus 1. I equal to n minus 1 is the last element. So here I'm removing AI. The left element after removal, the element to the left of removed element is I minus 1 and to the right is I plus 1. What I'm checking is if this is less than A of L is less than A of R, I am maintaining a variable which keeps the count of left and right contributions. If if the alternating property is satisfied, what I'll do is I'll increment the answer with PDP of L. Else I'll increment the answer with 1. Similarly, I'll also here I am adding the maximum contribution, maximum size that I can get from the left side. And similarly, I am doing the same. Here I am adding the maximum size I can get from the right side. And this is the case where AL is less than AR, and the case where the element at index L is greater than that at index R. Uh, the co logic is pretty much the same. Here only the signs will change. The signs will change because the condition to check alternating condition also varies, right? Here, if there is a greater than sign, then I have to have a less than sign here to have the alternating condition. And here also, I'm adding from the left contribution, and this is the right contribution of maximum size. And at every index that I have removed, I am taking the max possible answer. Like answer is max of the previous answer, comma current answer. Current answer is in the case when I have removed the element AI. Okay. And also we can note that here I have handled the case where we have no removals from the array. And that's all. Finally, I'm returning the answer. Here the time complexity of this solution is O of n because we can calculate this dp in O of n, and this can also be calculated in O of n. Here the max element function takes O of n time. And here also finally after every removal, uh, we are iterating over n elements. To be more precise, we are iterating over n minus 2 elements, excluding first and last element. And all the operations in this for loop is O of 1. So this also total for loop takes O of n time. So time complexity of this solution is O of n. That's all.